Okay, let's thank speaker and let's invite the speaker, and then Venka, you can go ahead.
Hi, my name is Venkat. I am a professor at the University of Illinois at Chicago. Today, I'm going to be talking about, I'm a system security researcher. I'm going to be talking primarily about the work that I have done in collaboration with some of the folks in this room about an approach for detecting advanced and persistent threats as part of DARPA's transparent computing program. And I will primarily summarize our work from a system security viewpoint, and then finally share my thoughts about where we are going with this and how AI research can help. Right. So just to sort of give some background on the problem, targeted cyber attacks on organizations are getting more sophisticated, stealthy, and serious. Generally, the goal of the adversary is to steal data, disrupt operations, or destroy infrastructure. And it's carried out over a much longer time frame, sometimes weeks, sometimes months, and they remain undetected most of the time. And it's often customized to the target rather than using some sort of commodity tools or malware. And thousands of incidents every year affecting large to small to large organizations. We heard about the Equifax, Marriott chains was attacked, and the cost could exceed 100 billion for the US economy. So I just quick summary of the state of art in this space. The APTs leverage different attack methods, span multiple applications and hosts, and enterprises today collect a wide variety of audit information like security information and event management and intrusion detection systems, application firewalls, identity and access management tools. All this is very useful, but it's hard to correlate information across these tools, and therefore when an attack happens, we can't really produce the big picture, right? And often this is done by cyber analysts involving a lot of manual effort to piece together all the information that these tools have. And so our goals are to automate this process. Analysts shouldn't have to manually search for interesting events, and we want to, and typically the information collected to assist this sort of scenario reconstruction consists of millions to billions of records. So how do we want to organize this information in such a way that we can produce the big picture? And we also want to produce sort of a compact summary of the causal chains that summarize the attack, enable, and we want to do this in real time so that an analyst can quickly ascertain whether there is an intrusion, understand the root cause, and determine the impact. Right? And also our goals are also to assist with cyber threat hunting. So when threat intelligence becomes available, we want to know whether a particular threat occurred. Right? So the main vehicle or tool that we use in organizing all this information from systems are provenance graphs. Very simply put, they are directed acyclic graphs whose vertices represent system entities like processes, sockets, files, and agents, users, and groups. And edges represent some sort of dependency relationships like information flow dependencies between say subjects and objects. Right? And the nice thing about provenance graph is that they sort of leverage the full historical context of activity in a system, and they reason about the relationships between different events and objects. Right? And primarily the provenance graphs in security have been used for forensic purposes. There has been some influential work back in the early 2000 and around that in using provenance graphs for forensics, but there are quite a few limitations. We are looking at a problem where the number of events that we have to process scales from hundreds of millions to billions per day, right? And to operate on these very large graphs might take hours or days to complete. It's not timely if we want to do real-time threat detection and forensic analysis. And there are, because the information collected is quite coarse at the level of audit records, there is also the problem of dependency explosion, where the graphs might include many irrelevant dependencies to the final scenario. So as such, provenance graphs have not found sort of widespread adoption in threat detection and forensic analysis, and but they are quite promising, and so we set out to actually use this provenance graph framework to actually do real-time threat detection and forensic analysis. So, so there are three main results, primarily from the DARPA Transparent Computing program, and now we are part of this program called CHASE. So the first is a paper that appeared in Unix Security for a system that we call Sleuth, and second is a system called Holmes that we published in Oakland this year, and third is another system called Pyro that is going to appear in CCS this year. So this talk is sort of a summary of these three results, what we have done with these systems, and also to show how AI can help advance the work that is laid by these systems. Right. So, so Sleuth was the first paper that we did as part of this project. So basically, the architecture of Sleuth looks like this. So we take audit logs from Windows, Mac, Linux, and there is also some implementation for Android, and we organize this as sort of a dependence graph in main memory, and then we define policies that trigger alerts on this graph, right? And once there are these alerts, so the graph that is laid in memory is tagged. It means that it has information flow labels, and that allow us to identify the root cause of the attack and also do some impact analysis. So once these alerts that are defined by policies are raised, we are able to traverse these graphs both forwards in time and backwards in time to identify the impact and the root cause respectively. So so what are tags? So for instance, subjects and objects are assigned trustworthiness and confidentiality tags, right? So there are different confidentiality levels. You can think of this more like the security labels work that was done in the 70s on multi-layer security and so on. So but here we have carefully curated these tags so that they work well for this problem. So we distinguish the notion of code trustworthiness versus data trustworthiness in order to control the propagation of labels. Processes have two tags, the code trustworthiness tag and the data trustworthiness tag. And as you can see, the separation aids detection and speeds analysis by focusing on a fewer set of root causes. And then we define confidentiality tags like secret, sensitive, private, and public, right? Now we define policies based on these tags that are then propagated on the dependence graph. So tag assignment and propagation are customized using policies. So for instance, the tag initialization rule might look like this. It might say that an object with a certain name is assigned a benign tag if it is from an internal IP address, or if it is from an external IP address, it's assigned the unknown tag, which means that it may be untrustworthy, right? And now when tags are initialized, they are propagated in main memory from input to output in the graph, and there are, of course, custom policies that override these, standard rules. So now we can talk about how we can detect attacks using provenance tags. So the approach is to focus on, the motive, to ask whether it is possible for an attacker to advance some high-level objective, like, run, some untrusted code, replace some, important files in the system, or do some data exfiltration, and means, can the attacker control, an action, right? Is the process performing an act that is untrustworthy, right? So the nice thing is that it is sort of doesn't require any labels. Once we define these very general policies, there are probably 6 or 7 of these policies in our system, then the reasoning happens nearly, automatically. There is no need for training, and assuming that the provenance data is not compromised, this sort of resists any adversarial manipulation. So so these are the main 4 policies in the system: untrusted execution, suspicious modification, data leak, and untrusted execution preparation. As you can see, they can be defined, fairly easily using the tags that we have set up. So so here is a small example where it shows the use of these. So here is Firefox that is actually downloading this file, bob crt1.o, that is then subsequently written to /lib, that gets linked to every executable that is produced by a user, Alice. Right? Now the tags allow us to capture these events as they happen in the audit records. So for instance, when the modification to the bash RC file happens, which then subsequently links this file to crt1.o, this produces a subsequent suspicious modification, modification policy. This raises an alert, and then there is the untrusted execution preparation alert when the loader actually links this file. So as you can see, all these alerts are raised, and we can traverse the graph, provenance graph, backwards to understand the root cause of this attack. So so now I just briefly talk about the kind of adversarial engagements DARPA did under this program. There was a red team that was tasked with producing APT-style attacks on a private network. And data, these attacks range anywhere between a few days to a couple of weeks. And the data was made available to performers like us, and we had to detect and report these attacks in real time. So this sort of gives some, this was only the first and second engagement that this system I'm reporting the results on. Subsequent, I will talk about some subsequent engagements later, but these were relatively short engagements. The longest running attack spanned 79 hours. Attacks were only carried out during the business hours of a particular day, and these were sort of the alarms that were raised when in that data. So as you can see, in 39 million events, we could see only 5 untrusted execution and 1 suspicious modification alarm. So fairly, the reduction in the amount of data a cyber analyst needs to look at is very significant, and we can then do the forensic analysis starting from these alarms. And so one common analysis that we do is the backwards analysis, whose goal is to identify the entry point of an attack. So the entry point is a source, which is in the provenance graph a vertex with in degree 0. And the starting points are the vertices that are suspect, marked by attack detectors. And the problem is to find source vertices from which a suspect vertex is reachable. The complications are that there may be multiple sources, multiple suspect nodes. So what we do is to define weights on this graph in such a way that it prefers shorter paths over longer ones, and prefer edges that correspond to a flow of untrusted code over untrusted data. And these preferences are encoded using some custom edge weights to Dijkstra's shortest path algorithm. And similarly, we can also do forwards analysis. The goal of forwards analysis is to see what the attacker did from a given alert point, right? So it is sort of an impact analysis. Backwards analysis identifies the root cause, right? So again, if we do a straightforward forwards dependence analysis, this might yield a graph with hundreds of thousands of nodes. So again, we have to be careful here. And so we define cost metrics where we follow the edge with untrusted code trustworthiness labels, where it is given a lower cost. And to some extent, we also follow the untrusted data labels, right? So once you do that, then the kind of scenario graphs that you produce doing both the forwards analysis and backwards analysis kind of summarizes the whole attack. So here is the final scenario graph produced from several millions of original records. So as you can see, the graph here, the circles are all the process names, the rectangles are all files, and diamonds are sockets, and the edges are directional. They denote the flow of information, and the numbers on the edges denote timestamps. So you can see that Firefox receives some data from a socket, and then it forks this executable called Mozilla Nightly, which goes on to perform some intelligence gathering in the system, like running a few system commands, communicating with an external IP address, and finally all this information is exfiltrated to another IP address in this edge 40. So all this information is summarized in a compact way in this graph. Here is another graph that was done on a set of attacks on a FreeBSD system. So here is a graph for attacks done on a Linux system. So in general, this is how our system reconstructs the whole attack campaign. You can see the number of entry points for Linux, for instance. This was a data set that had about 40 million records. The number of entry points, programs executed, key files involved, and most of them were sort of correctly identified, except for one instance where due to some label propagation there was some error, but otherwise. So the important thing was that none of the attack information was made available before the engagement concluded. So when we did the actual exercise with DARPA, we identified all this before any sort of ground truth became available. And then this is the table that compares the ground truth information with the actual detection results of our system. And we have done fairly well. So I think that sort of summarizes what we did with Sleuth. And now I'm going to just switch gears and talk about a second system that we built on top of Sleuth that we call Holmes, where Holmes, we have identified ways by which we can improve the detection accuracy by adding support for custom rules, right? So this appeared in Oakland earlier this year, and Holmes makes use of the insight that APT behaviors often conform to a certain kill chain, right? This is there are different kill chains out there in the literature, but this is the sort of prototypical one that was published by Mandiant, several decade back. So so we when we started this project, we did an analysis of about 300 APT white papers, and most, if not all, APTs conform to this kill chain, right? In particular, the high-level steps of a campaign are causally connected, and our insight was that we could use this connectedness between the high level steps as a basis for APT detection. So here is, for instance, a detailed provenance graph from a system where the activity in green represents the set of benign activities, and the activities in the red box denote the attacker activities. And as you can see, there is sort of the Nginx server that reads from an external socket and then makes a piece of memory executable representing sort of an initial compromise phase. And then there is CNC communication with the external world that denotes some sort of a foothold establishment stage. And then privilege escalation is performed so that the user gains access to super user privileges. There is Nginx then performs a number of commands that constitute some kind of internal reconnaissance, and then cleanup is done so that the tracks of the attacker are completely removed. And then finally Nginx exfiltrates all the data, sensitive data read from the system. So as you can see, the various phases of the attack as summarized in the high level steps below, they are all sort of connected in this picture, and whether we can use this connectedness as a basis for detection. So the key challenge here is how to fuse these point alerts representing various high level events into a strong detection signal. And if we manage to do that, we may be able to summarize the high level activities of the attacker in the form of these steps, and that may be even more useful to a cyber analyst than the kind of graphs that I showed earlier that were produced with Sloth, right. So the main approach is again to use information flow as a basis for alert correlation and campaign detection. So there is the set of audit logs that represent information in very low level events like system calls, and then there are these APT stages like initial compromise, established foothold, internal recon, and so on. So there is a big semantic gap between these ideas and the actual information present in the audit logs. So we bridge this gap by way of tactics, techniques, and procedures that is from the attack framework from MITRE. And we so once we describe the various tactic, techniques, and procedures that allow us to kind of seamlessly connect the information in audit logs to the high level attack steps. So so again we use the front end of the sleuth system. So there is the provenance graph laid out in main memory that allows us to do fast graph analytics, and then we describe the TTPs in that as matching rules on events described in the provenance graph. And once there are matches to TTPs, they are the connectedness between the various high level events is summarized in what we call the high level scenario graph, and we have a way of generating a signal from each of these high level scenario graphs, and once that signal crosses a certain threshold, we declare that a particular campaign is ongoing. So that is the high level idea behind Holmes. So here is a particular TTP example. So the initial compromise stage is on involving a certain process P, involves one of these TTPs. So for instance, there could be an untrusted read TTP where the read set of events constitute the event family, and this could be different for different operating systems, and this is relatively low. We associate a severity level with each TTP and then perform checks on what the prerequisites for matching this TTP are. In this case, we say that the socket needs to be from an IP address that's untrusted. Right? So likewise, there is a second TTP that describes when certain piece of memory is made executable, and the established foothold involves some shell execution TTP. So once we have sort of developed a system where this describes about 45 TTPs that capture a variety of common tactics used by attackers on these operating systems, And now, so one thing you may have noticed in the rules is that there are certain prerequisites for each TTP. So they include information that may be derivable from event arguments like file names and permissions, right? And they allow us to connect two different activities of a campaign and help reduce false alerts as part of a campaign. So an important problem to address here is the dependency explosion problem. Spurious dependencies can result in dependency explosion. And so we address this by asking a key question of and defining a notion of influence. We ask what is the influence that an attacker had in affecting any particular dependency. And so we develop a notion for any flow F or a dependence F. We develop the notion of ancestral cover, where we say a set of all processes that influence a certain set of dependency, a certain dependency F is the ancestral cover for F, and we want this minimal ancestral cover to be the number of minimum distinct compromises an attacker needs to effect in order to create this dependency. So the example is given here. So bash forks nginx, which then writes to nginx error.log. Then cat reads this file, and SSH forks cat. This is really a false dependency because nginx error.log is a log file that is affecting this dependency. Whereas look at this, Firefox forks bash and writes to recon.sh, which is then read by bash. This is something that an attacker who has compromised Firefox can easily control, as opposed to controlling this dependency of cat from nginx error.log. This may be very well be a benign activity in the system, but this is something that the attacker controls because attacker can actually fork bash and affect this dependency. So we in order to calculate these notion of influence, we define a condition called path factor, which is computed incrementally as we build the high level signature graph, and the value of this path threshold could be set based on the threat levels and organization phases. So for instance, by default, we can say an attacker needs to compromise at most 2 independent exploits in order to affect certain dependencies in an enterprise system, and that sort of works well, but more of this could be derived from empirical evidence data. And then we add a bunch of noise reduction techniques in order to generate a signal, a strong signal. So the idea is to exclude from benign matches to tactics, techniques, and procedures to reduce noise in the overall system. And so so what we actually get in the end is this high level graph that describes the various steps of an APT, and each of these internal nodes is actually a TTP, and you can see the edges of this high level graph are edges between the dependencies between the various entities here. So in effect, we are able to produce this very high level graph that summarizes the activities of a particular attack campaign, and we are able to compute a signal from it that says how confident we are that this actually represents a campaign. And that's where the severity levels of each of those TTPs actually matter. This allows us to convert any given threat into a numeric score, which we can then compare against a certain threshold. So so given any threat, we have a weighting function that allows us to compute an overall threat score, and then we use a standard severity score mapping that is published by NIST, but it could be any others based on empirical evidence, again based on data from actual attacks. So so we using the DARPA data sets, we measure the optimal threshold value, and also we deployed the system in a live detection setting where again in an engagement where we didn't know whether a red team is actually performing attacks. And here are some statistics on the provenance graph size. Since our provenance graph is mostly from sleuth, as you can see, it's the set of number of events. So for the topic size that is streamed in MB, you can see how the graph size grows, and this is the trace duration in terms of percentages, and these are the published records. So here is the high-level scenario graph of a Windows system. So it sort of here, these are all, there is a threat score that is computed directly from the scenario graph based on the severity levels, and the various labels here indicate, you know, the various objects that are there, and the events that were performed are labeled along the edges. And using the overall score that we compute, and we compare that against a certain threshold, and say that it's a, so overall our thresholds were somewhere less than 1,000. So, and this is well above the threshold, so we know that this is an attack. But at any point, the system keeps computing these high-level scenario graphs over and keeps comparing them against the threshold. And when the graphs, when the campaign meets that threshold, that's when we alert the user. So, I mean, this is an interesting graph that shows the effect of the path factor and the learning. We do some learning of the benign activity, and this box plot tells us what is the effect of doing these two. So, for instance, the green denotes the benign activity, and the purple denotes the attack activity. So, you know, without the learning and the path factor, as you can see, there is some overlap in between the benign and attack activity. But once we throw those things in, then there is a clear separation between the benign activity and the attack activity. So that's so this also gives the highest benign score in the data set. So you can see everything is the benign threshold. The benign score for all the high-level scenario graphs is less than 1,000, and for the various campaigns, you can see that this is really high. So this is one campaign where the score came fairly close to some of these, but otherwise everything is well above the threshold. The threshold was somewhere like 500. So we did some experiments to actually identify the optimal threshold value, but I will spare the details. So Holmes allows us to visualize the high-level APT in real time, and we mitigate the dependence explosion problem in the use of provenance graph by defining this notion of minimal ancestor cover, and we showed how effective these techniques are in against actual attack campaigns. I'm going to briefly talk about how we use provenance graphs for threat hunting in a system called Poiro, and this is work that is going to appear in 2 months in CCS. So, so often the question in threat hunting is about asking, anytime there is a published threat, you want to ask, have I been a subject of this threat, right? Has my enterprise been a target of this threat? And you know, the state of art is to look for indicators of compromise, like hash values, file process names, IP addresses, domain names, do some sort of you know manual or semi-automatic searches, and it's sort of limited against the use of you know legitimate looking names, or updated or repurposed attacks. It doesn't work, and any kind of polymorphic malware, this clearly doesn't work, right? And our thesis is that the relationships between artifacts and IOCs contain essential clues on the behavior of the attacks, right? And it's often tied to attackers' goals, which are often difficult to change. So what we want to do is to look for you know this behavior in the system's activity. So when you think of these large provenance graphs that contain millions of or billions of nodes. We want to look for a smaller subgraph that represents a certain thread. So for instance, here is a simple thread that talks about this process actually communicating with a certain external IP address, doing things to a registry, and interacting with the browser, and also interacting with a certain executable. Now this is sort of a thread behavior that is present in a certain malware. We want to know whether this was actually manifested in the system. And we want to do this in a matching efficiently, and so we are going to model this as a graph search problem. The provenance graph we call GP. It's a kernel audit logs modeled as a graph. We have used that in Sleuth and Holmes, right? And the attack graph or attack behavior graph is modeled as a query graph, which is much smaller. And both are labeled, typed, and directed. And we want to do sort of a look for a match, and this sort of match is not an exact match. It's not an exact subgraph match, but a match on flows. That is, we do want to allow for some approximate level of matching, right? And so this is how we set up the problem. So here are the indicators of compromise expressed. They are expressed as a query graph, and then the system behavior is captured from audit records as a provenance graph. And we describe the problem of graph alignment, where we look for an embedding of this graph inside the larger graph, right? And again, we compute an alignment score based on what we think are candidate alignments, and then we can, when that crosses a threshold, we raise an alert that a particular threat has been found. So I'm not going to talk in a lot of detail about this work, just give some very high-level thoughts, and then move on to the discussion part of the talk. So here is a query graph example for this thread. So this is the executable that is actually an executable that writes to a file C and then exfiltrates information to E, which is an external IP address, and D is some kind of a registry information. So the query graph can contain general terms like regular expressions like star, so that we can match even if there is a variant of a polymorphic malware that's performing these actions, the exact names don't have to match, and it summarizes the actual piece of malware. Now if you look at this is the provenance graph and this is the query graph, and we can identify that there are two possible candidate alignments here. So one alignment is, so the numbers on the edges are just for illustration. You can see that this is one possible set of alignments, Firefox along with these, and here is another possible set of alignments here where Firefox interacts with 7, the edges labeled 7, 8, and 9. So that's here, right? So the question is, which is the better alignment? And it turns out that this is the better alignment. It describes the threat better. But then how do we come up with these alignments, right? So again here, the key insight is to define a notion of an influence. How can an attacker affect a certain dependency in the provenance graph? And we do, since the flows are not exact flows that are described in the query graph, there could be multiple intermediate nodes in the provenance graph. We want to make sure that this is sort of robust against attacker actions such as forking multiple intermediate processes. So we define this notion of influence score, and then using this notion we define a metric called the goodness score that actually captures how good a particular alignment is. And this is the particular metric that we define for the goodness score that describes an embedding of the query graph inside the provenance graph. And we raise an alarm when the goodness score bypasses a certain threshold value. We did several experiments, one involving the transparent computing data and also with real world data incidents with publicly available language descriptions. And we set the threshold value to be 3, which means that we expect the attacker to have at most 3 independent compromises in the system. And here are some alignment scores for the TC data set. Most of these we were able to identify the alignment in one round. So we start by identifying some candidate alignments to the initial seed nodes, and then from there we search using the goodness metric on what are some additional candidate alignments. For most of these, we were able to identify them in one iteration. In some cases, it took 2 iterations. Here is an evaluation on certain malware reports. And the thing is that we did a comparison of Poirot with commonly available cyber threat hunting tools like Redline, Loki, and Splunk. The important thing to note is that those tools only use certain key indicators of compromise. So for instance, file names and hash values is used by Redline. Loki uses again the same thing. Splunk uses process names, and Poirot uses sort of a more of a behavioral graph matching. And so we were able to take all these isolated IOCs and piece them into a query graph representation and look for a threat and come up with a way by which we can do this automatically and conclude that the threat happened with a very high level of confidence instead of relying on sort of human intuition and manual verification. So that summarizes our work on Poirot. So I am just going to talk about some general thoughts on what I think are interesting. So we have worked with very large graphs. Some of these graphs are billions of nodes and edges. How can we how can the analytics take advantage of advances in learning? And one very simple thing that we can do, which is like really low-hanging fruit, is to automate construction of these query graphs that I talked about. So for instance, here is a natural language description that talks about email clients downloading Office Monkeys and video.zip. Office Monkeys self-extracts to Office Monkeys.exe, Monkeys drops Monkeys.exe and player.exe under temp. So as you can see, this sort of natural language description of a certain thread lends itself to a query graph representation, but perhaps one needs to build a good NLP based technique in order to automate this process. If this is there, then every cyber threat intelligence report and blog could then be converted into a mechanizable representation that we can search very fast. Right? It's fairly low hanging fruit. There is much work there, but this is something that if it exists, then enterprises would be able to search for threads in real time with the help of the main memory provenance graph, the query procedure of Poirot, and the mechanization of converting natural language descriptions to query graphs. Now we described how we can use a tag-based reasoning or information flow-based reasoning, and also misused rules like TDPs in threat detection. But it's likely that more sophisticated stealthy attacks that take advantages of well-known limitations of these approaches in order to stay under the hood, right? So anomaly detection, which has been studied well, offers an interesting midpoint in this space, right? How can we integrate anomaly detection along with the reasoning offered by these frameworks that involve information flow analysis and TTPs, right? So what is the role for learning based approaches? In particular, how do we combine tag based detection with anomaly detection? so that we can identify novel threats that try to stay under the radar of informational flow dependencies, right? So that's an open question, right? And often real world deployment of systems, often we get training, so we are talking about billions of event records of any sort of data that we need for training, right? We cannot guarantee that at any point that these training data are free of malicious attack. Attacks are omnipresent everywhere, right? So learning based techniques will acquire these attacks and conclude them as part of normal behavior, right? And it may be possible, so Tudor talked about poisoning, right? It may be possible for an attacker to slowly shift and in ways that we cannot detect, slowly shift the threshold of these detection techniques. Now the question is how to select features and learning methods so that they are robust to these adversarial actions. I think the use of tags and the use of reasoning about information flow might offer some interesting ways of thinking about adversarial robustness in these situations. So with that, I would like to thank DARPA for funding this research under the GC and CHASE programs, NSF, and collaborators from Stony Brook, Mohammed Hussain, Junav Wang, Scott Staller, and Sekar, and also my students and postdocs, Sadeh Milajerdi, and Brano Esate, and Rigal Jomimo. Thank you, and any questions? I'm happy to take any questions.
Any questions for the speakers?
So just a quick comment. I think some of the work that you're taking, very interesting directions you're taking the work in, of course with our collaboration on DC, but also with Poirot, where you're going. Just a couple of connections to make. You should also take a look at this work that was done for Watson for cybersecurity, which is around exactly this space, using NSV, which also you pointed out as a connection. But really where it brings together is consolidation of external threat intelligence, that's how we call it, threat intelligence, with internal threat kinetics. So threat kinetics is kind of the first part to show how the threat is actually generating in, evolving within the enterprise, and connecting it to the external threat intelligence that's coming in. And there are of course challenges at different levels there. One is of course the volume, the velocity, the variety of information that you're getting, with how to process that in an NLP in a timely fashion. But once you can get the subgraph out of that, as you're pointing out, which succinctly captures the given compromise, then you can actually do the graph. There's some very interesting questions as to what level you should do. Engineering, you made certain choices. The way you've done this, you said, okay, assume it's done, now you have this graph. How do I do this subgraph isomorphism and find this within the evolving part of the enterprise? But I think to make it applicable with practitioners are today they're sitting in front of a SIEM scheme. So Watson for Cyber takes a kind of a different approach. Jiong actually worked on this with Mark and others on that. Plus there's also a paper at Black Hat that Microsoft gave, was it this year?
Yeah.
Where they're also trying to go down this path of threat intelligence. And using NLP for threat intelligence definitely is an area for AI. I just wanted to give you that feature.
Actually, my student Sadeh, he interned at Microsoft with the same group. This, yeah, yeah, I think so. Yeah, yeah, he's, yeah.
Any more questions to the speaker?
So in your Provenance Graphs, show that you have these trusted tags on different websites, right? For example, Firefox might be a trusted application. If, say, your trusted application has vulnerabilities that somebody exploits, would that show up as an attack?
It depends whether the information, again, if you read from an untrusted, so typically a vulnerability, an application becomes vulnerable after reading some untrusted data. So there are tags that are associated with the untrusted data as it comes from, let's say, an external network. Then when Firefox reads it and then it performs an action, say it spawns a, it spawns a shell which goes on to do other things. So the tag propagation will capture, some of this. But if the, if the action happens in such a way where all the operations happen in main memory, then the kind of signal that we will get is weak. That is because the audit records don't tell you exactly what happens at the level of individual memory operations. They only tell you at the level of system calls. So Firefox may be tagged as untrustworthy data process, but that signal again is fraught with some limitations. So it really depends on the particulars of the threat, but the tag based reasoning does allow a way for you to reason about that particular situation. And this is where the distinction between code and data trustworthiness
Any more questions? If not, I guess everyone is waiting for the lunchtime. Thank you for the great talk, and thank you for the great work in the threat hunting and the threat detection. Thank you very much.